Good day, guys. I hope you're good. Welcome to Maths and Science series once again. This is the second part. If you didn't watch the first part, make sure that you do so. Today, we're going to talk about the Doppler effect of a moving sound source and a stationary listener. Now, as you can see today we're going to talk about the sound waves or the wave fronts. Now you can see the police vehicle inside the sound waves or inside those lines. Those lines are known as sound waves. Meaning, as you can see sound waves, it means that there is a siren or there is a sound emitted by the police vehicle or the sound source, the car. Then there is a listener. This is you on the right hand side of your screen. Now you can see the saying that the listener is stationary, meaning that he's not moving. Therefore, as he's not moving, it means that his velocity is going to be 0. Okay, now you can see that in front of the vehicle, the sound waves are closer together. It means that the wavelength in front of the vehicle in between the sound waves the wavelength is shorter, and behind the car the wavelength is longer. I hope you understand that. Why? Because the sound waves are not closely packed, but they are further apart or they are reflected. Therefore, to explain this, we can say when the sound source moves towards a stationary listener, as you can see. Why are we saying the sound source is moving towards the stationary listener? Is because the sound waves in front of the vehicle are closely packed. Therefore, when the sound source moves towards the stationary listener, it means that VL, velocity of the listener, is going to be 0. Therefore, the sound waves in front of the sound source are closer together, as you can see, and have a shorter wavelength. This is because the sound source is moving towards the listener. Now, where is the sound? Where is the wavelength? In between each and every line, as you can see, whether in front of the car or behind the car, those spaces in between these lines are known as the wavelength or the distance. So when the sound source moves towards a stationary listener, the sound waves in front of the sound source are closer together and have a shorter wavelength. This is because the sound source is moving towards that stationary listener. Then what you can actually discover here, or what you can conclude, is that the wavelength decreases and the frequency of the sound detected by the listener increase. I hope that makes sense. So since these sound waves are closely packed or are closer together towards or in front of the car or towards the stationary listener, it means that the stationary listener hears or detected a higher frequency. Therefore, FL is going to be greater than FL. Then that means that the listener or the police vehicle is approaching the stationary listener. I don't know, maybe he committed a crime, so they are coming to him and he's not aware. But you understand what I'm saying here. Yeah, so that's all. This is very, very important. They can actually give you a question paper showing wave fronts. So this information is very, very important. I hope you were noting everything that I was saying here. Now let's actually explain the other two scenarios, then we are done. And the most important thing before we can actually explain that other one, very, very important, you must know this. Don't forget to subscribe. All right. Here's another one. I won't actually explain much because it is the opposite of what we were talking about before. So when the sound source moves away from a stationary listener, the sound waves behind the source or the sound source are further together and have a longer wavelength. So the sound waves behind the sound source are further apart or are reflected. Then that means the wavelength is going to be longer. This is because the sound source is moving away. Then what can we actually deduce from that is that the wavelength is increasing and the frequency emitted or the sound detected by the listener is going to decrease. I hope that makes sense. But even let's say the vehicle is not moving, is stationary, and the listener is stationary, the sound waves are going to be equal. Now you can see that the sound source is stationary as well as the listener. Now what you must actually know here is that we have a uniform apparent frequency. Okay, so when both the sound source and the listener are stationary relative to the medium, can be air, nothing changes about the frequency you hear. Why? Because both the listener and the sound source are stationary. So what happens when both are stationary? There will be no Doppler effect. Why? Because when we define Doppler effect, we're saying Doppler effect is the change in frequency, but here there's no change in frequency, right? Therefore, there's no Doppler effect. Therefore, the Doppler effect is the shift you get when the source, listener, or both are moving relative to each other. But now, since they are not moving relative to each other, they are both stationary, it means that there's no Doppler effect. Now, if both are stationary, the relative velocity is zero. So the frequency shift is also zero. Therefore, there's no Doppler effect. I hope you understood this. So it's very, very important, guys. Very, very important. If you didn't actually understand everything from the beginning of the video, make sure that you rewind it until you understand it. So Doppler effect is a simple concept, or it's a simple topic, just need you to understand. And you can just go around, go outside that house, and maybe you can even go to the street to actually study Doppler effect. You can do it practically. Yes. So we'll end here. And please do subscribe to the channel. Do not forget to hit on the notification bell so that you can be notified when we upload new lessons. So and please like the video. Thank you.